All right, subscribers, welcome back to another episode of Science with Surbeck. Today we continue our review with our free response questions for the AP Chemistry test. And we take a look here into Unit 8 questions, which deals with acids and bases. And so for number 1, it says we need to answer the following questions about weak acids using the Ka values in the following table to help answer some of the questions. So in question 1a, it says using the expression Ka equals your hydronium times your conjugate base all divided by your weak acid, explain how to determine which solution has the lower pH, 0.1 molar hydrofluoric acid or 0.1 molar acetic acid. Now, it doesn't want you to perform any calculations. So a key thing with this is that we just need that explanation to explain, okay, how exactly is this answered, okay? So we start out here, and I'm going to transition to my answer sheet here, and I'd like you to write your answer on a separate piece of paper as well. And I'll start out here with 1A. So we take a look here. At our chart, and it says, all right, using the Ka, which one will have the lower pH? Well, as a reminder, as a review for acids and bases, the higher the Ka value, the lower the pH will be. So I'm going to pause, I'll write that down, and we will go through that here in a second. All right, so there is that statement that I just went over. And so if we take a look back on our Ka values are listed here. Now, remember, we're dealing with that negative exponent. So if we recognize which value is higher or larger, we notice that HF would actually have the larger Ka. So HF has the larger Ka because that value is the biggest of those two portions. So HF will have a lower pH because it has the larger Ka. Okay, so your Ka can be correlated to pH in our weak acids. Okay. Now we move on here to 1b. It says here which solution has a higher percent ionization, a 0.1 molar solution of acetic acid or a 0.01 molar solution of acetic acid. We need to justify our answer, including any calculations of the percent ionization for each solution. So with this problem here, we're actually going to have to perform a weak acid calculation. So I want you to keep this number for the Ka of acetic acid in mind as we go through this problem. So problem 1b says, okay, we need to recognize our acetic acid. And so what I'm going to do here is I'm just going to write the equilibrium expression for our acetic acid. So I'll start out here with acetic acid. And remember, since we're dealing with a weak acid, we're going to have to set up our ice chart, okay? So I'm going to start out this ice chart with the first value that was given. And looking off my sheet here, we have a 0.1 molar solution. So we start out here with 0.1 molar solution of our acetic acid. And remember, we don't need to worry about water. We don't have any initial H3O plus, and we don't have any acetate ion. Now the change, remember, is just going to be subtracting that X and adding that X on our acetate and our hydronium ion. Now at equilibrium, the expression would be written as 0.01 molar minus X, X, and X. Now what we have to do here is this. We have to set up our Ka expression. So our Ka expression is as follows. Our hydronium, H3O plus, times our acetate, C2H3O2 minus, all over our weak acid, acetic acid that is equal to that Ka. So what we need to do now is this. We need to plug our values here. We need to plug our values into our Ka expression. What we already have is the Ka. So the Ka, just reading it from the chart, is 1.8 times 10 to the negative fifth. Okay? This is equal to the value we have for our hydronium, which is X, and the value that we have for our acetate, which is also X. And then we have this. Our equilibrium value for acetic acid would be 0.1 minus X. However, remember, there is a little bit of a shortcut here, and that is this. If our Ka times 100 is less than our initial concentration of our weak acid, we can assume that 0.1 minus X doesn't need that minus X. So again, let me write this assumption so that we remember what we have to do to assume, and that is this. If we take our Ka times 100 and it's less than our concentration of acetic acid, then 0.1 minus X is really so small of a difference that we can just use our value here. And so again, assume that if Ka times 100 is less than the concentration of the acid, we can make an assumption about 0.1 minus X. So our Ka here is still that 1.8 times 10 to the negative fifth times 100, and it needs to be less than that initial concentration of acetic acid, which is 0.1. Okay, so what I'm going to do, I'm just going to throw these numbers into the calculator, and we're going to have 1.8 times 10 to the negative fifth times 100, and we get a value here, if we take it out as scientific notation, of 0.0018. So 0.0018 is less than 0.1. So that is true, right? I like to put a little check mark there to show that that is true. So then we can assume this, that 0.1 minus X is essentially equivalent to 0.1, okay? So that makes it really nice here. That means we don't have to use the quadratic equation. All we have to do here is put 0.1 as our concentration for our acetic acid. We don't have to do 0.1 minus X, but we do need to make sure that we make this assumption. Okay, so going through this process here, you would end up here with 1.8 times 10 to the negative fifth equals X squared over 0.1 as our value, okay? So now, here is this. Here's what I'm going to do. I'm going to solve for X. I'm going to skip some steps here and just tell you what our X is. Now, you need to go through and you make sure that your algebra is correct, but as long as you've done these steps, we should be good to go. So let me throw that in our calculator, and I'll take the square root of my answer, and our X, just for this value, is 1.34 times 10 to the negative third. Now this is equal to our concentration of our H3O plus. All right, so now percent ionization is the amount of original weak acid ionized. So the amount of ionized weak acid is shown here as this value of 1.34 times 10 to the negative third. So what we can do here is this. For our percent ionization here, we can take our amount of H3O plus. So I'm going to say H3O plus, the concentration of H3O plus, all divided by our original amount of acetic acid times 100, because we're expressing it as a percent. So this would be multiplied by 100. Now, what we can do here, I'm just going to insert my numbers, and we're going to end up with 1.34 times 10 to the negative third, all divided by 0.1, because that's our original acid concentration, and we multiply that by 100. So again, just throwing that into our calculator, we end up with 1.34 times 10 to the negative third, divided by 0.1, multiply that by 100, and we end up with 1.34% ionization. Okay, so our percent ionization of our acid is 1.34%. So I'm running out of room here, but our percent ionized is 1.34%. Okay, now it said we also had a 0.01 molar solution. So we need to do this process over again. I'm going to grab another sheet of paper to make this happen, and I'm going to move a little bit quicker. So I'm going to rotate my paper, and I'm going to pause and write my initial equilibrium value up here as well. All right, so I've set up our problem again. This time we have 0.01 molar acetic acid. So we have 0.01 molar acetic acid. Again, we don't need to worry about the water. And then initially we had zeros for our hydronium and our acetate ion. Now, what we need to do is this. Just like we did last time, we are going to associate the change, and the change is going to be the same. So we'll have 0.01 molar minus X, X, and X. Now, our equilibrium expression here is our Ka, which instead of writing that out, I'm just going to put 1.8 times 10 to the negative fifth over our hydronium, which is X, and we'll put that in brackets to represent that it's in molarity, times our concentration of acetate ion, all divided by our hydronium, or excuse me, our acetic acid, or the concentration. So 0.01 minus our X. Now, remember our assumption. We can assume that if Ka times 100 is less than our original concentration of acid, we can go through this process and we can say that 0.01 minus X is so small that we do not need to worry about that minus X. So Ka times 100, again, 1.8 times 10 to the negative fifth times 100, less than our initial concentration, which is 0.01 molar. Well, again, if we remember that our value here, 1.8 times 10 to the negative fifth times 100 is 0.0018. So 0.0018 is less than 0.01. That's good for us. That means we can assume that 0.01 molar minus X is really just equivalent to 0.01 molar. So when we write our expression, we can get 1.8 times 10 to the negative fifth equals x squared over 0.01. Okay? So when we go through this process, again, I'm just going to solve for x. Okay? So all I need to do here, I'll do this off the camera. I'll do 1.8 1.8 times 10 to the negative fifth times 0.01, and then I'll take that value there and I will solve for my x. And my x, when I put it into scientific notation, my x is 4.24 times 10 to the negative fourth, which is equivalent to hydronium ions. Now, our percent ionization here, our percent ionization is as follows. It is our amount of hydronium ion all divided by that original concentration of our acid. And we multiply it by 100. So our hydronium ion here was 4.24 times 10 to the negative fourth, all divided by our original acid concentration, which is 0.01 molar, and we multiply that by 100. Okay? So if we plug that into our calculator here, we have 4.24 times 10 to the negative fourth divided by 0.01. We then multiply by 100, and we get a value here of 4.24%. So our percent ionization is equal to 4.24%. Now, this means we can finally answer our question there, and that is this. It said, hey, which of those solutions has a higher percent ionization? Well, the answer to that is our 0.010 molar solution of acetic acid has our higher percent ionization. And again, by going through those weak acid calculations, that's how we were able to prove that mathematically. All right, so moving on here, I'm going to grab a new sheet of paper. I'm going to turn the page, and we're going to check out our part C here, or part 1C in our problem. So again, we start out here with this. I'm going to grab a new sheet of paper, and we'll start out with part C. And so part C says, hey, we have a titration graph or a titration curve, and it says a student titrated 50 milliliters of 0.1 molar solution of some weak acid with our strong base, sodium hydroxide. The results are given and shown here in this graph. And we want to know the approximate pKa, okay? So I'm going to be going back and forth, but for problem 1C here, and it's actually 1CI, okay? 1CI, it says, what is the approximate pKa of the acid? Well, the pKa is equal to halfway of the equivalence point. So let me switch papers here, and I'm going to pause and write that down. Okay, so just as a reminder, I'm not going to write this down, but the equivalence point is where the number of moles, in this case of base added, is equal to the number of moles of our acid added. And so at the equivalence point, you're going to have a dramatic change in your pH. So our dramatic change in pH is this big straight line in our graph. Now, roughly, we're going to estimate this, that our equivalence point is at 25 milliliters. Everyone see that? We have our line that we have the dramatic pH change, and it's right here at 25 milliliters. So again, we have this. Our equivalence point is when we have 25 milliliters of our base added. Now we need to take that statement that I just wrote up above, and we need to think about this. Okay, if the equivalence point is 25 milliliters, we need to get halfway. So our halfway point is this number, 25 divided by 2. So at 12.5 milliliters of NaOH added is equal to halfway of the equivalence point. Okay, so now what we need to do, this is an estimation from our graph, but what we are going to do is we're going to go to 12.5 milliliters of NaOH added. And luckily for us, it's right here in between 10 and 15. And what I'm going to do here is I'm going to make another mark, and then I am going to estimate the pH, okay? Now this is an estimation, all right? So again, if we scroll over, and you can look on your graph, if you scroll over, again, we are right here at 12.5 milliliters of NaOH added, and we go to the left. It's a little bit above 3. I'm going to call that a 3.2. So at this, our pH is equal to about 3.2, and at that halfway point, this value of the pH is equal to our pKa. So our pKa is about 3.20. Again, this is estimated because we just looked at it at the graph. So we're going to say our final answer here, roughly the pKa is about 3.20 because your pH is equal to your pKa halfway at that equivalence point. Okay, a lot to take in there, a lot to consider. Things that we've gone over. Now, question 2 is a little bit easier here, or question 1C2. It says, what specific value from the graph is needed in addition to the information in part C to calculate the molar concentration of NaOH? Well, again, this graph is relative, so we would need the exact value or volume of NaOH added. So again, for 1C2 here, we would need the exact value or need the exact volume of NaOH added. Again, we estimated that it was 25 milliliters. Okay, moving on here. Again, we have another hypothetical question here for 1C3. It says, identify a pH value between 2.5 and 7.5 at which the concentration of the weak acid being titrated is less than the concentration of the conjugate base. All right, so I'm going to start out here with our formula that's known as the Henderson-Hasselbalch equation. And the Henderson-Hasselbalch equation says our pH is equal to our pKa plus the log of our base over our acid, okay? So now what we can do here is this. We want to be able to have a pH value between 2.5 and 7.5 in which that concentration of that weak acid is less than the concentration of our weak base. Well, let's remember this, that at our pKa, the amount of acid added is the halfway point of the amount of base added, or excuse me, the amount of original weak acid is halfway to the number of moles of base added. Okay, so for this process to happen here, your pH needs to be above your pKa value, okay? So for this to happen here, our pH needs to be greater than our pKa value. And what that does at this point, when your pH is above your pKa, this causes your concentration of your base to be greater than your acid. So I'm going to draw another arrow here. At this point, when your pH is above your pKa, your concentration of your base is greater than the concentration of your acid. And if you want to try that, you can go through and do some calculations, but it all deals with logarithms in this point here. So anything here, to answer part C here, any pH, a pH greater than our pKa value, which we established in earlier parts, so pH greater than 3.20 would result in more conjugate base than acid. Okay, so again, these are all hypothetical. Now we can get to some calculations here that we will use to go through this particular process. All right, so I'm going to change papers here, and we're going to go over this problem here. So it says, in another experiment, our student titrated 50 milliliters of 0.1 molar acetic acid with 0.1 molar NaOH. Calculate the pH of the solution at its equivalence point. So I'm going to grab another sheet of paper, keep that one handy there, and we're going to go through this process. First off, we once again are dealing with our acetic acid. So we start out here with our acetic acid, and we draw our equilibrium expression. And we end up with something like this. And what we have to be aware of is what's happening as we go through our titration. Well, here is a key word to this, okay? What we did is we titrated to this equivalence point. So what's happening is this. If we start out with 0.1 molar acetic acid, and all of a sudden we've gotten to our equivalence point, we've added enough moles to essentially eliminate our acid, okay? So what happens is this. If we think about our equilibrium expression, we would get this. At the equivalence point, the number of moles are equal, okay? So at equivalence point, moles added are equal. So instead of putting 0.0 or 0.1 molar, I'm going to find out how many moles did we have to start with. So to find the number of moles, all we need to do is we need to take our concentration in liters times our molarity. So 50 divided by 1,000 to get us into liters times 0.1 is 0.005. So what I'm going to do here is this. Instead of putting 0.01 molar, I'm going to put 0.005 moles of acid added. Okay, so this means at the equivalence point, moles added are equal, or moles of NaOH specifically added are equal. So this means that if we added enough strong base to this strong acid, we have eliminated we have eliminated or neutralized our acetic acid. So at our equilibrium, we have none of this value. We have added our moles of our acid, and more importantly, we have added 0.005 moles of our particular weak base, okay? So I'm going to concentrate on this because we really got to get going after this. At our equivalence point, we have 0.005 moles of our weak base. Yes, we would have some of our hydronium ion, but what we need to do here is think about this. All of this hydronium is reacting with our other substances, so we need to highlight, we need to concentrate on this. At equilibrium, we have 0.005 moles of our acetate ion, okay? Now, we have to also think about what we have in our solution. If these two molarities are equal, that means we added equal volume. So what I want to do, or what we can do out of this, is we can find the molarity of C2H3O2, and that would be equal to 0.005 moles all divided by 100 milliliters, which is 0.001 liters. Okay? So we have 0.005 divided by 0.1, and we get 0.05. So we get 0.05 molarity, and now we can actually start our problem. So now, because we've eliminated all our weak base, and essentially at equilibrium here, because we're at the equivalence point, we have no hydronium ion, we actually have a weak base problem to deal with. So here we go. You know, we're starting it off here. We have C2H3O2 minus, which we just took the time to figure out what was our molarity, plus our H2O as a liquid, and we have some we have our weak acid, and we have our hydroxide. Okay? Now, we just took the time to calculate, hey, what was our initial amount of our weak base? Well, hey, it's 0.05 molar. Now, initially here at this problem, we didn't have any of these substances here. So we go through this and we establish our adding our variables. And so at equilibrium, we'd have 0.05 molar minus X, X, and X. So now, check this out. This is a weak base. So it'd actually be Kb over our concentration of weak acid times our concentration of OH minus. All right? This would all be divided by our weak base. Now, hold on a second, because our Kb was not given in this problem. However, check this out. We have the Ka. Okay? So the Ka is this. Our Ka can be used to find our Kb. So remember, what we have here is this. Our Kw is equal to our Ka times our Kb. So Kw equals Ka times Kb. Well, our Kw, remember, is 1 times 10 to the negative 14th, equal to our Ka, which is given in that chart at 1.8 times 10 to the negative 5th, times your Kb. So your Kb value, after you do all this calculations here, would just simply be 1 times 10 to the negative 14th divided by 1.8 times 10 to the negative fifth. And we get a value here. I'm going to round to three significant digits. Our KB would be 5.56 times 10 to the negative 10th. So in this case here, when we set our problem up, it would be 5.56 times 10 to the negative 10th equals our x squared from x times x, all divided by 0.05 molar minus x. But wait, we can assume, right? Our assume, in this case here, our assume is going to be this. KB times 100 should be bigger, so KB times 100 should be bigger than our concentration of our base, okay? Or excuse me, smaller. And if we take a look here, our KB times 100, I have that plugged in our calculator, times 100 is very small, all right? So this checks out. That means 0.05 minus x is essentially equal to 0.05. So we can do this. I'm running out of space here. We can do this. Since 0.05 molar minus x is essentially equal to 0.05 molar, we can eliminate our value here. So I'm just going to go ahead and get rid of that due to some space. So all I'm going to do here, I'm going to just solve for x. So we take our KB times our 0.05, and then we put that into our x, and we get a value here of 5.27 times 10 to the negative 6. Now, x is equal to the concentration of our hydroxide, and so we just calculated it to be 5.27 times 10 to the negative 6, and we can calculate the POH. So the POH is the negative log of our value here of 5.27 times 10 to the negative 6. And when we do that here, I'm going to write it down below, our POH is as follows. So negative log of 5.27 times 10 to the negative 6. It would be our 5.28. But wait, that is our POH. The problem wanted pH. So the pH, remember, is equal to 14 minus our POH, which was 5.28. So to find our pH, all we do is we take 14 minus 5.28, and we get a value there of 8.72 as our problem. So the key thing here on this problem here is remembering, at the equivalence point, all of this weak acid is used up. The only thing that we have left in solution is our weak base. It becomes a weak base problem. We can solve, or we can find KB using our KW equation, and then we just go through, we solve for x. The only thing you need to really take into consideration is you're solving for that pH. All right, so I hope you've enjoyed this problem. I know there's a lot to it. There's a lot to acids and bases, but go ahead and review how to complete these problems. And as always, I hope you have enjoyed this episode, and make sure you subscribe if you haven't already.